So welcome to this lecture on multi-core scheduling, and we'll also look at multi-resource scheduling. So in multi-core or multiprocessor scheduling, the basic idea is quite simple. You have a single dispatcher queue into which all your jobs enter, and then they are distributed into the different CPU-specific run queues. So every CPU has a run queue, and a run queue traditionally does not have a space between run and queue. So you have different CPU-specific run queues where your work is kind of dumped there. And then you have a CPU-specific scheduler, which runs one of the algorithms that we studied in the previous lecture, right? So that's what happens. So given this, we have to now create a new set of definitions for multi-core scheduling. So what we look at in this case is actually Cmax, right? So this is our heuristic. So assume there are M processors. And let's say this axis is time. So what happens is that I can schedule one job, then one more, then one more. And then let's say something else, one job and one more and one more. So finally, if I have a set of jobs, which is typically the case, if I have different P threads, right? So finally, what matters is the maximum completion time, which is Cmax. Is that correct? That is what matters, right? That is the maximum completion time, because by this point of time, all the other cores would have completed their work. We just want to find the slowest, the laggard in that sense. So that is why, so this is known as the Makespan. If I were to kind of draw the computations as a graph, it would be the longest path. So this is known as the Makespan, right? Cmax. So clearly, even in multiprocess, preemptible variants are much easier to schedule than non-preemptible variants, which are mostly NP-complete. So we will look at this, but the basic idea here is to minimize the Makespan. So if let's say P means that I have P processors, I have more than one. If preemption is allowed and I want to minimize Cmax, then actually I have a very trivial algorithm. My trivial algorithm is that I take this and I simply, ensure that the work that all of them do is exactly the same. And how do I do that? Well, I just chop jobs. Preemption allows me to chop jobs and create as thin slices as possible, right? So I just add up all the jobs lengths, divide it by M, and then just assign that much of work to each CPU, right? And after that, you can just chop it and move it to another core. And given that we have assumed that the latency is low, migration latency is 0, and context switch latency is 0, arriving at this solution is actually quite trivial. It's very easy. But if I take out preemption, this becomes NP-complete. This is normally the case that when preemption is taken out, then all hell breaks loose. So the two problems that are typically used to prove NP-completeness in the domain of multiprocessor scheduling are bin packing and partition. So in bin packing, we have a finite number of bins. So assume that, each one of these, if you have M cores, you have a finite number of bins, right? And the size of each bin, let's say in this case is Cmax. Well, let's say in this case, the size of each bin is lambda. We'll relate lambda to Cmax very soon. Each bin has a fixed capacity. Let its capacity be lambda. There are n items. In this case, one item is a job. Each item has size Si, means each job has a duration Pi. We have to pack items into bins without exceeding their capacity. This is the same as saying that without exceeding a known Cmax threshold, which in this case is lambda, and given the fact that there is no preemptions, which would be tantamount to cutting an item and putting part of it here and part of it there, if I were to just pack these boxes with items, which is nothing but jobs, and no cutting is allowed, I want all of them to fit within the bin size of lambda. So this is the decision problem version of the NP-complete problem, where the idea is that are they fitting or not? All right. So in this case, if you recall in an NP-complete problem, if I give you a proof, you can verify that it's a proof in polynomial time. If I give you a solution, you can verify it's a solution in polynomial time. But arriving at it is a separate thing. For that case, no algorithms are known. So in this case, you can clearly see that the scheduling problem, where lambda is nothing but the Cmax threshold or the bin size, and in this case, just packing the bins, which is the same as assigning a job to a core, they are equivalent problems, right? Bin packing and scheduling with Cmax as the objective function, the Makespan as the objective function, they are equivalent problems. Does that make sense? Okay. Given the fact that that makes sense, then you can see that, for proving something that is NP-complete, what you say is you take a known NP-complete problem, which in this case is bin packing. Every instance of a bin packing problem is converted to an instance of a multi-core scheduling problem. In this case that we have done, we take an instance of bin packing and we say that the max bin size is, let's say, my Cmax threshold. Of course, I convert it to a decision problem. So in this case, the decision is that if Cmax is equal to lambda, is my system schedulable or not? Correct? So that is my decision version of the problem. So in this case, what I do is the size of every bin is lambda. Every job is an item. Instead of size, I say its size is its execution time. And then I take every bin packing problem and map it to a scheduling problem. So this mapping is such that all the problems have an analog over here, which basically means that if I'm able to solve scheduling using a polynomial time algorithm, multi-core scheduling, I can solve bin packing using a polynomial time algorithm. So you know that if A implies B, then not B implies not A, right? So this would mean that, I have a scheduling algorithm I have a polynomial time algorithm for scheduling. This would mean I have a polynomial time algorithm for bin packing. But because I don't have something for bin packing, I don't have something from here. So that's the typical NP completeness reduction that you do. All right. So which means that if bin packing is NP complete, multi-core scheduling without preemption with Cmax as the objective function is also NP complete. Similarly, the other problem is partition. Right? So you can easily, prove that partition is NP complete by doing a reduction from bin packing. So here you say that consider S, that is a set of numbers. You find a subset of S. Let's say the set of numbers are 2, 4, 5, 7, 9, 12, 13. You find a subset of S whose sum is equal to a given number. Let us say you find a subset whose sum is equal to 24. So 5 plus 7 plus 12 is 24. So this is your partition problem. Of course, you can always say you can have an equal size partition, or you take the overall sum divided by 2 and say find a subset whose sum is this, but this is a more generic variant of it. It's also called a subset sum problem, where I want a subset whose sum is equal to a known number. In this case, the known number is 24 and there is a solution. But let's say if I take a million numbers and I say find a subset whose sum is something, that is an NP complete problem. So this problem is also used to prove that a lot of the scheduling variants, right, are actually NP complete, right? Both the bin packing problem as well as the partition problem, because you see partition is what? Partition is you are basically saying that, if let's say I want the sum of all the jobs, execution time, sum of the execution times of all the jobs, I want it to be, let's say, 302, which means I need to find enough jobs whose sum adds up to that. Correct? Are you sure I'll find? That's an instance of the partition problem, which is why this is right, given that the partition is NP complete, again, any scheduling problem that relies on this also becomes NP complete. So both of this sum total of the argument is that in any non-preemptive setting, it is computationally hard to ensure that a CPU is doing a fixed amount of work, because you will end up running afoul of either the bin packing or the partition problems. And given that, no polynomial time algorithm is there for those, you will not be able to create a polynomial time algorithm for these as well, right? So let us now look at heuristics for multiprocessor scheduling. So we will look at list scheduling. So list scheduling can come in many types, but almost all the types share some common features. So we maintain a list of ready jobs. So all the jobs that can currently be executed, we maintain them. And we sort them according to some priority scheme. It does not matter which priority scheme, but some priority scheme. So when a CPU is free, what it does is it searches this list and finds a job to execute. Okay, so whatever some job it will find to execute, but the constraint is there is no idling. In the sense, if there is a job, the CPU will not decide to idle. All right. So if it has work to do, it will definitely do it. It will choose, it will never make the choice of not doing anything. That is a key constraint. So then it will preferably pick the job with the highest priority. But again, as I said, the priority scheme in this case is not strictly necessary. There is no idleness. We assume that the machines are identical and the scheduling is non-preemptive. So there is no preemption, right? So this was your NP complete version, right? That there is no preemption. Assuming all of these things, we can create many different list scheduling strategies, not one, but many. One of them is that I can take all the jobs, order them in descending order of processing times. I can do that. So the longest running job I can do first, or I can do it in a reverse manner. If I can create a graph of jobs, like this job is dependent on this and then this on this, I can take the longest path in the graph and say that this is the critical path, so I'll execute all the jobs on the critical path first. Then I can maybe look at all the jobs, sort them in terms of their out degree. Why is the out degree important? Because if a job is done, it will enable the maximum number of succeeding jobs, assuming there is a dependence between them. So sorting them on the basis of the out degree actually makes sense. So I can do that. So there are many results which say, so all of these problems are NP complete. But there are many results that say that they can be made near optimal. How near optimal, we will see. So we'll first look at a result which says that the computed makespan is often less than 2 times the ideal makespan. So specifically, if I have n jobs and m CPUs, the scheduling problem I'm looking at is P, then there is no constraint, so there is no preemption, right? And then I want to minimize the makespan Cmax, and I'm interested in this ratio Cmax by COPT. I want this ratio, so I claim that regardless of whatever priorities you assign, as long as there is no idling, R is less than equal to 2 minus 1 by M. So we will prove this. If I sort the jobs in descending order of execution times, and then I take the longest job first and then smaller, then R is less than 4 by 3 minus 1 by 3M. All right. So this is my scheme. So what we will do now is that we will maybe prove the first. The proof for the second one is there in the references if you look at the book. So what is the first result saying? The first result is saying you take any list scheduling scheme subject to the fact that there is no idling. The ratio is bounded by 2 minus 1 by M, where M is the number of CPUs. All right. So let us do one simple, so proving this is not very hard at all. So let us take the same diagram that we have been drawing. Time goes up. So let us say I have M CPUs. So consider the case where all the jobs I'm able to schedule and they are perfectly balanced, in the sense that this is the second CPU, I schedule this job, perfectly balanced, right? Which means that all of them finish at the same time. So then this duration, let me say it is capital L. Then this is the optimal Makespan, because the point is that no further packing can be done because there is no wastage. So C opt is equal to L, right? What is the total amount of work that you are doing? The total amount of work that you are doing is M times L, right? That is the complete work that you are doing. So this is, let's say, your ideal case. Now let us look at a more practical case. So if you look at the practical case, what is the worst case, right? So the worst case will be when, let us say, so with no loss of generality, what I can say is that all of these finish, right? All of these are balanced. Balance means the same, right? And then we have some job here, and then we have some more job here, all right? So this is the worst case, because basically what I'm doing is that there is clearly an imbalance, okay? So of course, if let's say any of these bars kind of cross this boundary, it's fine. But the point is that in terms of imbalance, this is perhaps the most unfair that everybody has done. And, well, this is the most unfair everybody has done, but one of them has extended. Now the question is, how much will it extend, right? That is the key question, that how much can it extend? So what we would like to do over here is that the work done in this case will be the same. The same amount of work will be done, all right? And let us say that what is the maximum duration of this job? It is equal to L, which is C opt, because the worst case, you could have this job, maybe the entire thing is being done by one CPU. So the maximum duration of this offending job can be equal to C opt, right? It can't be more than that. So then this I can say is L plus ML minus L. Is that fine? Okay. So this means that the work done in, the other part, if I just ignore this job, over here, is ML minus L. So the point is, how much is this distance over here? This distance D is basically ML minus L, right? Divided by M, all right, because it is fully packed. So this is L minus L by M, all right? So what is Cmax? Cmax in this case is equal to, this distance is D, this distance is L, D plus L, which is equal to, D is L minus L by M plus L, which is 2L minus L by M, which is equal to L into 2 minus 1 by M, all right? So this is your Cmax. So Cmax by COPT is basically, COPT is L, this is L into 2 minus 1 by M. So Cmax by 2 OPT is actually less than equal to, because we considered the worst case, 2 minus 1 by M, which is exactly the relationship that you have over here. So this is one way of sort of easily proving the approximation ratio of a simple heuristic in list scheduling. What is it that we use? Nothing but a little bit of arithmetic and mathematical jugglery. And we were able to show that regardless of the strategy that you choose, COPT is of course optimal, but arriving at that point is NP complete. But if you choose Cmax using a list scheduling approach, then you will be within a factor of 2. 2 minus 1 by M to be precise, but broadly speaking within a factor of 2. In fact, it is further possible to do even better if, let's say, you take the execution times of the jobs into account. In that case, you will be within a factor of 4 by 3. So now we will look at a multi-resource scheduling case. And so we have looked at complex schedules where we have different arrival times, preemptions, deadlines, priorities, dependencies. Also, you can have CPU affinities. So CPU affinity is again a multi-core multiprocessor concept where you say that the ith core should only run these threads. So this thread should only run on the ith core. All right. And this thread should only run on the jth core. So there is a set affinity function in Linux where you can see if you are scheduling, kindly ensure that this thread has a preference for this core. All right. So that is an affinity. We looked at different metrics. We looked at mean completion time, Lmax, and Cmax, which is the Makespan. In the case of multi-core scheduling, we looked at all three. What about the correctness? Well, we have to ensure that there are no deadlocks. So for single copy of the resource, we have done. But for multiple copies of a resource, so let us say you have 3 printers. Let us say you have 4 scanners. In such a situation, these things are much harder. So we will see that a circular wait is not an issue when you have multiple copies of a resource. In the banker's algorithm, we consider multiple copies of resources as opposed to a traditional deadlock detection algorithm where you consider a single copy of a resource. So let us consider multiple copies and we shall see that circular dependencies are not a problem. They do not pose a problem. So let us assume there are 2 types of resources, class A and class B. There are 2 resources of type class A, 2 resources of type class B. At a given point of time, process P1 has locked 1 instance of A and 1 instance of B. So 1, 1 is locked and 1, 1 is left. Out of that 1, 1, process P2 has locked 1 instance of A and process P3 has locked 1 instance of B. So basically all 4 instances are locked, and furthermore process P2 desires an instance of B, but that it will not get because there is no free instance available. Instead, let us assume it is waiting on P3. Alright, and then you assume that P3 desires 1 instance of A where it is waiting on P2. So in this case, what will happen is, it is true that there is a circular dependency, but this will not lead to a deadlock. The reason it will not lead to a deadlock is because when these 2 resources are released, then they can be given to P2 and P3 respectively. So that's the reason circular dependencies. Also, there are different ways of drawing this graph. In one way that we have drawn, it appears that there is a circular dependency, but of course we could have drawn these differently. We could have drawn it this way and we could have drawn this way. In that case, there would have been no problem. But the main thing is that if there are many ways of drawing edges, it would be unfair to expect someone to actually draw them in such a way that there is no cycle, because that itself is not an easy problem to solve. So it's a much better idea that we devise some sort of an algorithm that, in spite of such dependencies, sees if there is a way to provide resources without a deadlock. So in this case, clearly we will satisfy P1 first because it is the one that can be immediately satisfied. A greedy approach can be followed. Once the resources are released, they can be given to P2 and P3, and we can satisfy the requests of P2 and P3. So such sort of an example motivates us to understand the logic of the banker's algorithm, which basically follows a greedy approach, where the idea is that you satisfy whatever request you can, and then you will release the resources that are currently held. That will increase the available resource pool. Then probably you can satisfy more requests, so on and so forth, until you are able to satisfy all the requests. In case you aren't, then you can say that clearly the situation is not desirable, in the sense there are a set of requests which are not satisfiable and the state is not correct, right? So we will distinguish a safe and unsafe state later. But broadly speaking, this is the insight that we can gather from this slide. So let us look at the data structures in the banker's algorithm. So if we have n processes and we have m types of resources, so basically the algorithm for deadlocks in a multi-resource scenario is known as the banker's algorithm. All right. So let us say that you have m types of resources, not m resources, but m types. So the available array will have one entry for each type of resource, where available I means that you have these many copies of the resource I available. All right, available for acquiring, available for locking, whatever. Then you have a max matrix. It's a matrix, okay? So essentially you have n rows and m columns, and process I can request at the most max ij copies of resource j. So this basically says that the ith row corresponds to the ith process, the jth column corresponds to the jth resource. It simply says, or processes declare a priori how many copies of a resource they will at the most request for. Acquire is again a matrix. This is basically how many copies have you actually acquired. As process I, how many copies of resource j has it actually acquired? That is there in the acquired matrix. All right. So max is the theoretical maximum, and practical maximum, and acquired is how many have currently been acquired. Then you have a need. Need is essentially max minus acquired. All right, so acquired plus need is equal to max. So let's say I can acquire 5 copies maximum, and I've currently acquired 3. Then that's all right. My need is 2 more. All right. So max, acquired, and need are a process specific view. So there may be 20 copies of a resource, but my max may be 5. I may have acquired 2, so my need is equal to 3. But available is the total number of copies of the resource in the system. So available is process independent. All right. So you need to remember these 4 things. Available is system specific. Max, acquire, and need are matrices, but available is a vector. And these are process specific. All right. So these are our broad state elements that we will have in the banker's algorithm. So the first thing is, if I want to check if the system is in a safe state. A safe state means that whoever wants whatever, can the allocations be made, or am I in a deadlock situation? So we look at a bunch of algorithms, they are all more or less the same, right? And so let us see. So available is basically this: how many copies of the resource I are currently available. Okay. So this I create a local copy of it, I put it in current count. All right. So current count is basically saying at this moment, let's say for the ith resource, how many copies are free, right? That is current count. It's just a copy of available. And for every single process, there are n processes, I say I'm not done. So done is false. Then I run a for loop. I run a loop. So I try to find a process I, and I means process I. Such that done I is false. I'm not done with it, right? And my needs, whatever I need, subject to the fact that I will acquire my maximum, my stated maximum, is less than equal to current count, which means that whatever my requirement is, that is less than the availability. If that is the case, then I go to the next step. If such an I cannot be found, I jump to the last step, which is this step. All right. So what is it that I check? I check that as a process, I'm not done. Second, whatever is that I need, that my needs are currently available. All right. If that is the case, if I'm able to find such a process, then I jump to this line. In this line, what I do is, I assume that my request is satisfied. Hypothetically, I assume that my request is satisfied. If my request is satisfied, then whatever I have acquired, I will return that back to the pool because I am done, right? So whatever I have acquired, which is ith process, whatever I have done, I will return it back to the pool, right? Free pool of resources. So this I will return, it will go into current count. All right, so current count will become plus equal to, which means that, for the ith process, its requests were satisfied. So whatever it had already acquired, those are returned back because it's done, right? Then I will set done I to true, meaning for the ith process, I am done. Again, I will come back, again try to find a process with unmet requirements. It is possible that there was no process earlier, but because I returned a few resources, now suddenly this condition is true for some process. Could be the case. No problems, I keep doing it. I keep iterating, I keep repeating until I reach the last step. When do I reach the last step? When no such I can be found. At this point, we expect all the processes to be done, which means everybody's requirements have been satisfied. If that is not the case, then I am unsafe. If it is the case, I am safe. This is same as hypothetically, conceptually a deadlock detection, where it is just possible to satisfy everybody's request. That's all. It is just holding in a multi-resource scenario. So the complexity of this is order of mn square, and the reason is very clear. We need to take a look at this operation over here, where the entire loop runs n times. For this check, we actually need to look at the requirements of every single process. Again, another factor of n. And for the requirement, we are essentially operating it with m element vectors. So that is a factor of m, which makes it order of mn square. Next, we can think of a resource request algorithm, where I will request for some resources, the system will check whether the request should be granted or not, which basically means whether the system will kind of go down to become an unsafe state or not. So the rec array is an array of resource requests, right? For, let's say, So say rec j is equal to k, and of course, so rec array is specific to a process I. So if it should be like this, say if rec j for process I is equal to k, it means process I needs k copies of resource j. So rec is technically a matrix, but in this case, we are thinking of it as kind of one row of that matrix, where we are saying that this is for a certain process. So I can say it is like this, and I can write it like that. So it is k copies of resource j. Broadly speaking, that is what I want, that is my requirement. All right. So first is you can do a basic check. So clearly rec, if this is greater than your need, it is violating the contract. Because need is basically saying how much more you will require subject to your pre-declared maximum. If it is more than need, then clearly it cannot be satisfied because you are violating your contract, where you said that at the most you will acquire these many copies of a resource, and now you are violating it. So you can't request more than your need, right? That can never be done. Then, if request is more than available, then there is an issue. Why? Because you don't have the resources. That is why it is an issue. Otherwise, what you do is you do a dummy allocation. You assume that the request is allocated, given. So from available, you will have to take out the rec resources. So available will reduce. You will give it to acquired, right? And you will reduce your need. All right. Then once you have done that, right? So once you have taken it out from available and you have added it to acquired and removed it from need, then this becomes a new system state, right? You will check if the system is still safe or not, which means is this leading to some sort of a deadlock kind of situation, right? And if it is not safe, you have to undo the current allocation and you will have to wait, right? There could be problems. So you will have to undo it and wait. So it's a nice way of checking for safety. The next is a deadlock detection algorithm. And so in the case of a deadlock detection algorithm, again, we'll use a very similar line of thinking. So all of these algorithms are quite similar actually, right? So think of Rex to be an n cross m matrix where n rows, one for each process, m columns, one for each resource. And the ijth entry basically says how many copies of resource j does process I actually require. So we will do the same. We will set the current count as available. And then for all I, if let's say I have not acquired anything, so basically if I have not acquired anything, then my done is true, which means I'm not interested, right? This is what it means, right? That I am not interested. Otherwise, if I'm interested in resources, my done is false, which means I need to go through the loop. Then what I do is I try to, so this part is exactly the same. I try to find an I which is not done and whose requirements are less than the current count. If let's say there is such an I, then you go here and then you assume its request is satisfied. So whatever it has acquired is given back to the pool of the current count and you set its done to true. So finally you keep doing it until you don't find any entries and you do exactly the same check. If let's say all the processes are, all of their requests are satisfied, there is no deadlock. Else, there is a deadlock because there is some process whose request I cannot satisfy. All right. So broadly speaking, it is the same, the same thing keeps repeating, the same kind of thinking, right, broadly. But this is the basic idea that you try to see if you can satisfy everybody's requests. You cannot satisfy, this means that I need something, someone else needs to release. So there is some sort of a constraint which is not satisfiable jointly. That is why, and that is a deadlock in a multi-resource scenario, where everybody's request cannot be satisfied, regardless of the order. All right. So what happens if you find a deadlock? So then the first thing is that you can, Banker's algorithm is basically a deadlock avoidance algorithm. So it is not allowing a deadlock to form in the first place. So what we are doing is that, let's say before every request, if we check and let's say we see a deadlock is forming, we may delay the request, we may cancel the request, or we may kill a process. All of these things are doable, right? Because the main idea is that you do not enter an unsafe state. Because you know that if you have entered an unsafe state, then problems can happen. That is why another thing could be you deliberately enter an unsafe state and keep performing these deadlock detections. So it all depends, but if you want to run an avoidance algorithm, you don't enter an unsafe state, which means that there has to be a way to actually deny requests, right? If a request is kind of potentially deadlock forming, you have to somehow deny it. You have to somehow say no. If you do that, it is good. Otherwise, if you detect a deadlock, something has to be done. So then one of the processes has to be killed, its resources has to be released. That is kind of a sledgehammer way of dealing with a deadlock. But broadly speaking, if you have a deadlock, nothing can be done. It is just that the Banker's algorithm gives you sufficient warning in advance that this request is taking you to an unsafe state, you don't go there. If you still don't heed to the advice, then if a deadlock forms, then the only option that is left is to actually kill a process and release its resources. So this current lecture ends over here. In the next lecture, we will discuss scheduling in the Linux kernel. So we will look at the algorithms that Linux actually uses. So the CFS algorithm, a completely fair scheduler, is what we will look at. And then we will cover a little bit of real-time scheduling, and then this chapter will end.